Welcome to the video presentation for Team 5, Designing the Automated H-Track System. Our team members are Jacob Anderson, Brandon Frieden, Mike Mudanu, Alex Seeley, Dustin Sorensen, and Mihir Pimpal. We are advised by Dr. Andrew Merriweather with additional assistance by Dr. Rosenbluth and his team at the University Health Department. The goal of the project is to redesign traditional H-Track healthcare lift systems with more autonomy. Current systems rely on healthcare workers to physically manipulate the patient and lift. The benefit of an autonomous system would lessen healthcare assistant workloads and provide greater independence to patients who experience restricted mobility and dexterity. Our project focuses on three tasks: the system's ability to identify a chosen object as its target, locate the target in three-dimensional space, and execute motor commands on a scaled H-track frame. Prototype success is dependent on the accuracy and precision of these three components. Object detection is provided by an open software program named YOLO5. The chosen object to be the target patient lift point is a generic climbing carabiner. Multiple photos of the target were created in an image library which the software, through machine learning, develops the ability to detect the target from an input image and outputs the target's pixel coordinates. The carabiner went through design changes involving its color, finalizing on a red paint. 3D spatial measurement is done with a Microsoft Azure Connect depth camera. Given an input of the target's pixel coordinates, the camera measures a 3D vector and the software outputs the target's location in Cartesian coordinates. The scaled H-track frame was designed to replicate the structure of existing H-tracks, with a dynamic crossbar and a motorized trolley which travels perpendicular to the crossbar motion. Custom components were fabricated to replicate the full-size concept, which requires power to be delivered from the trolley itself and the crossbar attachment points. The system was fully tested in Dr. Merriweather's lab using a Vicon motion capture system. The mocap system is able to provide sub-millimeter accuracy of marked objects in 3D space. Marking the system subcomponents of the carabiner target, depth camera, and frame trolley, the system's precision and accuracy can be determined by contrasting the prototype's results against the mocap results. Testing was conducted with three variables: lighting, target position in the XY plane, and target orientation. The data sets to analyze were target location relative to the depth camera, the trolley's final position relative to its preceding motor commands, and the trolley's final position relative to the target location in XY space. Testing the object detection separately, a test was done in order to determine the effect of lighting, distance, and orientation. The test was a degree of error experiment. A total of 24 images were tested. The YOLO5's centroid was compared to the target's true center, and the amount of false positives and false negatives were recorded. The first goal to discuss is the accuracy and precision of the trolley to move to a position given by the Arduino code. Our metric for success is the trolley's error must never be greater than 1 centimeter from the desired position. The trolley was sent between distances of 5 centimeters to 70 centimeters, each distance tested with 5 trials. From the figures to the right, you can see that the error was never greater than 2.6 millimeters, meaning we successfully achieved this metric goal. The second metric goal is the accuracy and precision of the depth camera. Over 12 trials, the 3D vector measured by the depth camera was compared to the associated 3D vector from the mocap system. The goal was to keep error in any direction less than 5 centimeters. The result table on the bottom right shows the maximum radial error to be 4.94 centimeters, deeming success in achieving this metric goal. The third metric goal, and final for distance metrics, was the ability for our YOLO5 program to accurately and precisely target the image pixel corresponding to the target center. Success criteria is error no greater than 5 centimeters. The carabiner target was imaged with all possible combinations of light levels ranging from 0 to 100 lux, distances ranging from 35 to 245 centimeters, and the target orientation ranging from 0 degrees to 90 degrees. This 8-image process was done over 3 trials. Illustrated in the figure to the right, the maximum mean error was the carabiner with 0 degree orientation, close distance, low light level. The value of 2.33 centimeters meets our criteria and makes this experiment a success. Our YOLO 5 image detection model was put through another round of testing, as it was observed that the room lighting was the greatest influencer of detection failure. Our room space was set to a lighting level of 0 lux, and the variables tested were distances and confidence. The confidence of the YOLO 5 is how strict or picky the software is when predicting a found target. A lower confidence level of 0.1 to 0.4 will be more acceptable to declaring a false positive as shown in the left photograph. A high confidence level up to 0.7 will be very discriminatory and can lead to more false negatives as shown in the right photograph. Two trial sets of 176 images each were analyzed. Our goal was a 95% positive object detection rate. Observe the upper surface plot. As the YOLO confidence is lower past 0.6, false positives occur at all distances from the camera. At confidence rates 0.6 and higher, there were 0 false positives. This would be a promising performance of the system. However, as shown in the bottom surface plot, a confidence level of 0.6 and higher fails to positively identify a true target at greater distances. Using the confidence level, which yields the least amount of failure, the system was only able to positively identify a valid target 89% of the time. This makes our prototype insufficient in achieving its tasks in dark settings. In summation, does our prototype system accomplish the 3 key component tasks? Does the YOLO 5 program detect the target? In well-lit settings, yes, but in dark settings, system performance was substandard and does not meet the design goals. Improvements will have to be made. Luckily, with YOLO 5, the target object is customizable, and there is a possibility of using the depth camera's IR filter to detect reflective targets in the absence of light. Does the depth camera get an accurate and precise distance to the target? Yes, and it is sufficient for larger room scale operations, and it does have the option of being trolley mounted, if desired, in full-scale prototypes. Does the trolley get overhead of the target? Sure does, but major design changes are needed for a true full-scale prototype. We came under budget, and an information package has been created for new users, specifically subsequent design teams, to incorporate this hardware and software into their work on the project. This concludes the video presentation for Team 5, H-Track Lift.